Today we will see one more random process which is known as the Poisson process. Poisson process. Poisson process. Okay, this is one of the important random process type of random process, and in this random process, basically it is a counting process. Okay, it is a counting process. That means it counts the number of arrivals. Okay, that is, it is a counting process. It's also known as a counting process, and it will counts the number of arrivals. Okay, it will counts the number of arrivals. Okay, what is was it what do you mean by this? That means, suppose you are having a time axis. Suppose you have time axis. It starts at 0 seconds, for example. Okay, and you are considering a queue. Okay, there is a queue. Okay, for example, you can consider in the airport, you are in the queue like this. Okay, so in a queue, suppose nobody was there. Okay, now after some 2 seconds, after some 2 seconds, one guy came, so he is in the queue now. Okay, now after 3 seconds, that means at the third second maybe two peoples came. Okay, two peoples came at the fourth second. Okay, at the fourth second, maybe one more guy came, like this. Okay, the peoples are coming from here. Okay, so this random process usually represented as x of t, where x of t means x of 2 second is nothing but that there is only one person. This is the person. Okay, and x of 3 seconds is nothing but you have two persons here and one person here. So 2 and 1, so 2 plus 1, you have 3 persons in the queue. So x of 4 second means you have one more guy here. That means you have 1 plus 2 plus 1, that means 4 persons in the queue. So in general, x of t actually represent the number of arrivals. That means you can see here the number of it is the number of arrivals, or you can say, or number of peoples in the queue here in this example, number of peoples in the queue. So this is basically representing, so this kind of random process is known as the Poisson process. Okay, it is known as the Poisson process. So it is actually representing the number of peoples in the queue, or number of total number of arrivals. So this is representing, we can say that it is representing the total number of arrivals. Okay, so in another way, another example we can see here, for example, suppose in the regarding the telephone call. Okay, telephone calls to an airport, for example. Suppose you are considering about airport, and at the beginning of the day, let's say from 8 o'clock, from 8 a.m. I am recording, I am counting the number of calls. Maybe after some time, say that this is I am considering this at the time 0. Okay, at time t equal to 0, I am counting at some I am starting my counting at 8 a.m. So I will assign this time as time equal to 0. At after some t1 second. Okay, and you are dividing the interval into t1, t2, t3. Okay, or let's say I am dividing my interval. Let's say this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, and so on. Maybe between the 1 and this is the first minute, for example, minutes, this is the second minute, so this is in minutes. Okay, in minutes in general. So in the first minute, somebody has called in between the first minute, so I will represent this by using an impulse function. Okay, this I am using by representing by using an impulse function. So this is representing impulse function, and another guy is also coming in between. Maybe in between 2 and 3 you may get 2 calls. Okay, after one call you may get another call also. So here you are getting 3 calls, let's say. Okay, and maybe one call here, maybe one call here. So how many calls you are getting? You have 1 2 3 4 5 6 7 8 9. Okay, so at the 6th second, suppose you are considering x of 6 or 6th minute. Okay, you can see here this is 1 2 3 4 5 6 7 8 and 9. So you are getting 9 calls. Okay, you are getting 9 calls. So this kind of random process which completely represent the, which counts the, that means the random process which counts the number of arrivals in a particular amount of time. Okay, you are considering here 6 minutes. That's it. Okay, so in a particular amount of time, is called the Poisson process. Okay, this is called the Poisson process, and usually represented as x of t. So we can represent the Poisson process. Okay, and here this is showing actually the arrivals. But the Poisson process will count the total number of arrivals. Okay, so it is counting the total number of arrivals. Actually the Poisson process is counting the total number of arrivals. So how we can count here? In this case, you can see here, this is the time axis. Let's say this is the time axis for the above example. For this example, suppose this is the time axis. Let's say this is time t equal to 0, and this is 1, and this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Okay, 7, and this is 8. Okay, this is the time axis. And the Poisson process basically represent, I told you, it is counting the total number of calls. So how we can represent? If you integrate this, this is showing, actually basically I am showing an impulse function. So we can integrate this. So at some time here you have an integral which is 1 and between 1 and 2 again, so you have one arrival here. Again between 1 and 2 you have again 1. Okay, I have only the space here, so I will reduce the magnitude. This is 1. So at time between 1 and 2 you have one more arrival, so it become 2 now. Okay, now between 2 and 3 you have 2 arrivals, so become 3 and then become 4. Then you have between 3 and 4 you have 3 arrivals, 1 2 3. Okay, so 5 6 7, it becomes 7 until between 4 and 5, and between 4 and 5 you have one more arrival, so it become 8. Sorry, not here, it become 8. Okay, after that between 5 and 6 you have one more arrival and it become 9. Okay, so this is showing a random process x of t, and this is nothing but the Poisson process. Okay, so this is the graph of this x of t for a, this is the sample function. You can say this is a sample function. Okay, now we want to find out how we can this is a counting process basically. Here you can see that the events are happening in a discrete way, but this graph is showing a continuous random process. Sorry for this. So we have okay, so we have now we will represent how we can look into this in another way. Okay, let us consider the time intervals. Let's say you have time intervals 0 1 2 3 4 5 6 7 8 9 10 and 11. So here you have 11 intervals. Suppose you are considering the whole duration of these intervals as t. then the duration of each block, suppose you are considering this as one block, then duration of one block will be nothing but t by n. So t is representing the whole duration and t by n is representing, it is the duration of each block. Okay, it is the duration of each block. Okay, and as n tends to infinity, you know that as n tends to infinity, the block duration or the duration of each block, the block duration will tends to 0. Is it clear? So with a fixed t, with a fixed t, so you can divide the whole time interval. Suppose you have the time interval t, you can divide into small pieces, very small pieces. As you increase the n to infinity, then the duration of each block will be tends to 0. That means you will be getting a continuous time approach if you increase the number of values of partitions, number of partitions. Okay, so as n tends to infinity, you will get a very small block duration. That means the block duration will be very small. The block duration will be very small. That means you will be approaching a particular time instant. Okay, you will be approaching a particular time instant. In that situation, you may get sometimes, that means you will get a time instant. Let's say time instant, you will get a time instant t, basically in general you can say. So a particular time instant, okay, you will get a particular time instant. So in that time, suppose, what is the probability of getting an arrival? That means you have two situation, basically. You have two situations. Okay, that means you may have an arrival. That means you will get an arrival. Yes, that means somebody is coming into the queue. Or you may not have an arrival. That means no arrival. So you have an arrival or you may not have an arrival. There are two situations. We have already seen something with two outcomes, that is known as, basically, if we have two outcomes, that kind of phenomenon can be modeled by using the mass function, by using the binomial distribution. We have already seen this in the first few lectures. So binomial distribution. So this will be, so at a particular time instant, it will be taking a form of binomial distribution, right? So it will be taking a, it will be a binomial random variable, we can say. This random variable, we can say it as a binomial random variable, because we may get a arrival or not an arrival. Okay, so what is the probability of success? Suppose we want to, what is the probability of arrival? Success means what? So we have already told you, this is which can represented by using a binomial random variable. So this arrivals, that means we can have an arrival or no arrival. So this situation can be modeled by using a binomial random variable. So in a binomial case, we should define something known as P. What is that P? P is nothing but the probability of success. That means probability of success means what? There is an arrival. So success means here it is representing an arrival. Okay, how we can define this? Suppose lambda is the arrival rate. That means number of arrivals in 1 second. Okay, suppose I am defining a factor lambda, which is nothing but the number of arrivals. Okay, or lambda, it is the average arrivals rate. Okay, not average. Okay, it is the arrival rate. Sorry, it is the arrival rate. So lambda is the arrival rate, which is represented by using number of arrivals divided by the time. That means number of arrivals in 1 second. So we are considering a small block duration with like this, with n equal to 11, right? So each block will be having a time duration t by n. Okay, t by n. So how many arrivals we can expect in this particular block? That means our block duration is very, very small. So the number of arrivals we can expect, the number of arrivals we can expect in this small duration, in this small duration, let's say this small duration is delta d. Okay, this small duration expect in delta d is nothing but, we have the number of arrivals in 1 second into that duration. Okay, that means which is equal to lambda into t by n, right? So the number of, that is the probability of having an arrival, that means the probability of success or the probability of arrival. This success we can represent also as arrival. The probability of arrival we can represent, probability of a successful arrival we can represent it as lambda into t by n. I hope this is clear to you. Okay, so this is how we can represent, and lambda is the rate of arrivals. Okay, lambda is the arrival rate, which is represented as number of arrivals divided by seconds. Okay, so this is the idea. So we can represent the Poisson distribution as the Poisson process. We can represent the probability mass function for the Poisson process as the probability that x of t, that means the total number of arrivals. What is x of t? I have already represented it. X of t is representing this type of graph. That means at particular time, suppose you are considering the third second, for example, then the value of x of t is 4. You can see. What does it mean? There are 4 peoples in the queue. That's it. So the probability of x of t, which takes the value k, that means there are k peoples in the queue. For example, there are k peoples in the queue. Okay, that is the meaning. That means x of t take the value value k. Sorry. So there are, you can see here x of t takes the value 4. And what is the probability of this x of t takes the value 4? That's what we are going to write. It can be written by using the probability mass function, which is defined as lambda t. Okay, lambda t into whole raised to k into e power minus lambda t divided by k factorial. Okay, divided by k factorial. Okay, lambda t, sorry, okay, lambda t, this is I am considering a particular duration, capital T, or in general, if I am using capital T, this is the, I am using here capital T also. So in general, I can represent, so we were talking about this duration, the whole duration was capital T. That's why we were talking about this. Suppose you are considering a time instant, general time instant T. Okay, now you can divide the whole thing into small block. Okay, so that the block duration delta D is tending to 0, and the block duration will be delta D will be equal to T by number of pieces. Suppose n is the number of pieces, so T by n. So in such case, you can represent the probability that x of t takes the value k is nothing but lambda into t whole raised to k into e power minus lambda t divided by k factorial. Okay, so this is the formula, general formula, for the probability mass function for the Poisson process. So this is the PMF of the Poisson process. We will prove it anyway. So we are going to prove this. So proof for P of x of t is equal to k is having lambda t whole power k into e power minus lambda t divided by k factorial. So we are going to prove this guy. Okay, prove this. So let us consider the continuous arrival in time. So let us consider the continuous arrival in time. Okay, that is, we have 0 and some people are coming into the queue like this. Okay, so this is showing each arrival. So I told you that the sum, because this is the arrival at I have already told you that arrival at each time instant takes the form of binomial. It is take the form of the Bernoulli random variable. Bernoulli random variable. So we can see that the sum, that means the total number of arrivals, that is the total number of success. We have seen while tossing a coin consecutively, the total number of success, the total number of success can be represented by using the Bernoulli or binomial distribution. So this is a Bernoulli random variable. So we can represent the total number. We can represent total number means sum. The sum of successes or means sum of arrivals. We can represent by using, can be represented by using the Bernoulli random process, or we can say binomial distribution. Okay, so we will assume that if the block duration tends to 0, then we will get our approximation become exact. Suppose we are considering, I told you this is the blocks. Suppose you are considering a time 0 to t and you are dividing into small block. Suppose this block duration, if the block duration delta d, which is nothing but t by n, tends to 0, when it will tends to 0, as n tends to infinity, number of partitions tends to infinity, then our approximation for the total number, that means the sum of successes by using the binomial distribution, become exact. So first of all, we will represent by the total number by using binomial distribution. After that, we will put the limit that number of n will tends to infinity. Then our approximation become exact. That is the idea. Okay, so we are going to represent. So let us consider we have a time t, and this is time 0 and t equal to 0 and time t equal to t. So we have we are observing at this point, let's say. Okay, and there is an arrival here there is an arrival. Okay, and there is an arrival here, there is an arrival here, and there is some n. But as n tends to infinity, then we will get very close points. That means delta d, that means the block duration will tends to 0. What is that? Delta d, t by n tends to 0. So then what is the situation? Like this it will proceed. Then you can exactly see there is only one arrival in this duration. So as the block duration tends to 0, It's very, very small. As delta D is very small, we can expect only one arrival, right? Because the block duration is very, very small. So we can expect only one arrival. So we can model this by using the binomial distribution. Okay, binomial distribution. This is representing the binomial distribution. Okay, so you see here we have small blocks. Let's say this is first block, this is the second block, third block, like this. Okay, so in this block, if there is an arrival, you have number 1. If there is an arrival in this block, if there is one arrival, you will get 1 plus 1, you will get 2. If there is another arrival here, if there is no arrival, you will get again the value 2. If there is an arrival here, so like this, there is an arrival here, there is an arrival here, there is no arrival here, there is an arrival here. So you are actually counting the successes. You are just counting only the successes. So this can be modeled by using the binomial distribution. Okay, in binomial distribution, in this duration, okay, in delta D, that means T by N, okay, in this small duration. So the probability, so if you are counting like this, at the end of the day, for example, this is let's say this is showing the first n equal to 1, this is showing n equal to 2, this is showing n equal to 3. So the probability at nth block, probability that x of n takes the value k, you can represent this by using this guy, that means the binomial distribution. Okay, so the probability that x of n takes the value k, because in a small duration you can expect only one arrival, that means it can be either true or false, that means a person may come or may not come. So the probability of x of n takes the value k is nothing but n choose k, that we have already seen in the first few lectures, p raised to k into 1 minus p the whole raised to n minus k, and k takes the value 0, 1, 2, etc. Okay, so up to n, because you may get okay, that's it. So okay, this is not so important here. Anyway, so probability of x of n is, so that's it. So probability of x of n is equal to k is n choose k. But you know that the probability of arrival is p is nothing but the probability of arrival in duration delta d, and we have already seen this. As in the form, yes, this we have already seen. It is nothing but the probability of arrival is lambda into t by n. So this t by n is the duration of the block. Okay, here I have shown you the total duration was t, but in our case the total duration is small t. So it is nothing but lambda into our total duration is small t. So, and this is starting at 0. So the total duration is nothing but small t. So the block duration is nothing but lambda into block duration. Okay, so this is nothing but lambda into t by n. So our p is nothing but lambda into t by n. I hope this part is clear to you. Now we will substitute this. So the probability that x of n takes the value k is nothing but n choose k into p raised to k into 1 minus p whole raised to n minus k, because we can get n arrivals, because you see here we are splitting into total n blocks. So in each block maximum we can expect one arrival, right? So total arrivals, so maximum of k is nothing but n. So you can expect maximum n arrival, that means k may be 0 or 1 or 2, or maximum it may go to n. Okay, So now we will substitute here. So the probability of x of n takes the value k is nothing but n choose k into lambda t, because p is nothing but lambda t by n whole raised to k into 1 minus lambda t by n. This is our p whole raised to n minus k. So this is actually representing, that is, this is representing the probability of k arrivals. Okay, at probability of k arrivals at nth when we view at nth block. That means what will be our time t? Our time t will be duration of each block into n. So at t is equal to delta d into n, right? So duration of each block is delta d and delta d into n. So this is nothing but the probability of k arrivals. So we will now represent, but our block duration, as the block duration delta d tends to 0, we will get a continuous time. Okay, we will get an idea about the continuous time counting. Okay, that means we will get the continuous time, because our time become continuous, you can say. The time become continuous. Okay, so as delta d tends to 0, we will get the continuous time. Okay, and as delta d tends to 0 means t by n tends to 0, that means that our n tends to infinity. So we are going to put here limit n tends to infinity. The probability of x of n takes the value k is nothing but the probability of x of t takes the value k, because our time become continuous now. Time become x of t, sorry, x of t, it is not x of t. So our time become continuous, because we are talking about the continuous time process. So continuous time process. So the probability that x of t takes the value k is nothing but limit n tends to infinity. We have this thing, it is nothing but n choose k into lambda t by n whole raised to k into so as the time become continuous, that means limit n tends to infinity, n choose k into lambda t by n whole raised to k into 1 minus lambda t by n the whole raised to n minus k. So this how I can write like this. Okay, that means it is nothing but the probability that x of t takes the value k is nothing but limit n tends to infinity. N choose k is n factorial divided by n minus k factorial into k factorial into lambda t, sorry, it's lambda t divided by n whole raised to k into 1 minus lambda t by n whole raised to n minus k. So this is nothing but the probability that x of t takes the value k is nothing but limit. I told you there is n factorial. So n factorial you can write like this, n into n minus 1 into like this into n minus k plus 1 into n factorial, sorry, not n factorial, n minus k factorial, n minus k factorial. So this is how you can write this guy. That means you can write the n factorial. Okay, you can write this n factorial like this. Okay, and divided by, you can see here there is a term n minus k factorial. So n minus k factorial, okay, into k factorial, and there is another term which is, you can see lambda t, you can see here lambda t by n whole raised to k. So it become actually lambda t whole raised to k divided by n raised to k. That means n into how many times? That means k times. Okay, then there is a k factorial. This k factorial I will move here. This is k factorial. Okay, multiplied with, then another terms remaining is 1 minus lambda t by n whole raised to n minus k into 1 minus lambda t by n whole raised to n minus k. So I can write like this, whole raised to n divided by 1 minus lambda t by n whole raised to k. Now I can rewrite this equation. X of t is equal to k is nothing but limit n tends to infinity. You can see here it is nothing but, first term you can see there is n here and there is n here. So n by n, then n minus 1 by n, like this it is going, then it is n minus k plus 1 by n. So there is some term here like this. Okay, then it is multiplied with, you can see here this two things will be cancelling. That means there is n minus k factorial, sorry, and here there is n minus k factorial, it will cancel, into lambda t whole raised to k divided by k factorial multiplied with 1 minus lambda t by n whole raised to n divided by 1 minus lambda t by n whole raised to k. Now we will see what will happen to the first term. You see here n is very large, so limit, I will take this term, limit n tends to infinity, n by n, n minus 1 by n, and so on, n minus k plus 1 by n. This will tend to 1, this will tend to 1, this will tend to 1. So this guy become 1 anyway, double. Similarly, this no change because there is no factor n here. And what about this thing? What about the third one? You can see here this is having something, okay, the third one I will take. That means this we are going to consider now. We are going to consider this factor. Okay, what will happen? Now you see here, so it is nothing but limit n tends to infinity 1 minus lambda t by n whole raised to n divided by 1 minus lambda t by n whole raised to k whole raised to k. Okay, so you will get here this factor, for example, this will be tending to, this will become, there are some mathematical proof for this will be tending to e power minus lambda t into 1 power k. Okay, that means this will be nothing but e power minus lambda t. I am not going to the mathematical proof of this. So we can write the total. So we obtain the final answer. So we obtain, after this substitution, we will obtain the probability that x of t takes the value k is nothing but lambda t whole raised to k divided by k factorial into e power minus lambda t. This is what we have seen, and for t greater than 0. So this is what we have seen, and this is the probability mass function of the Poisson process. Okay, and if you take the expectation, the expected value of x of t is nothing but, you will get lambda into t, and the variance, we are going not going to the proof, variance of x of t, which is nothing but the variance of x of t, you will get again it as lambda t. So the mean and variance of this process is same. So I hope you understood this proof. Now let us consider another thing. Let us consider you have the whole time duration. This is starting at 0 and at time t1, okay, and this is at time t2, and you want to find the number of arrivals. Anyway, there are number of arrivals at t1. Suppose you have I peoples in the queue. It is the I is the number of peoples in the queue. Okay, now at x of t2, what is the probability that it is j? Okay, so the question is the probability that x of t1 is equal to I and x of t2 is equal to j. So one of the important point you have to note that all these intervals, these two intervals, this is interval 1 and this is the interval 2, you have to note that this interval 1 and interval 2 are independent because it is not depending. Okay, so this is nothing but, you have probability that number of arrivals at time t1 is I, and because they are independent, you can multiply the individual probability. That means you should have I arrivals, you should have I peoples in the queue at time t1, and between these time, what is this time in between these two? It is nothing but t2 minus t1 is the time. So the time difference is t2 minus t1. That means x of t2 minus t1 between this time, you should have, we are talking about j here. So if it is j, it is always increasing process. So how many peoples will be coming? There are j minus I arrivals. So j minus I arrivals in t2 minus t1. So it means that I peoples at time t1 and j minus 1 I peoples come again, that means arrivals in time t2 minus t1. So that is what I have represented here. So how to represent? So the probability of x of t1 is equal to I and x of t2 takes the value j is nothing but the probability that the number of arrivals x of t1 is I multiplied with the probability that x of t2 minus t1 is j minus I. So this we know the formula. This is nothing but lambda into t1 divided by I factorial, this raised to I, into e power minus lambda into t1 multiplied with, we know what is, instead of t we have t2 minus t1. So lambda into t2 minus t1, okay, whole raised to j minus I arrivals j minus I arrivals divided by j minus I peoples, j minus y I factorial into e power minus lambda into t2 minus t1. So that's it. So this is the probability. This is how we can find the probability. So with this notion we will see a problem anyway. So this is the example 9.21 from the textbook. So this is the problem. Okay, you can see here the inquiries arrive at a recorded message device according to the Poisson process. So there is a recorded message device. For example, if you are calling to the customer care and all, it is a recorded message will be coming. So it is talking about those kind of machines. That means the inquiries are coming to that machines. That means the peoples are calling at each and every minute, you can say. Sometimes nobody will call, sometimes you may get a lot of calls. That means the inquiries are arriving at a recorded message device according to the Poisson process. That means this is an arrival process, so we can represent by using a Poisson process at a rate of 15 inquiries in 1 minute. That means the arrival rate we can calculate. Arrival rate, you have 15 inquiries. Arrival rate means lambda. Okay, arrival rate lambda is nothing but you have 15 inquiries in 1 minute. Since you can see here our question is nothing but find the probability that in a 1 minute period 3 inquiries arrives in first 10 seconds and 2 inquiries arrive in the last 15 seconds. That means in the first 10 second, you have 3 inquiries. That means 3 arrivals, 3 inquiries, and in the last 15 seconds, that means this is 60, so maybe starting from 45. So this is the last 15 second. It is talking about 2 inquiries. So in this duration you have 2 inquiries. Okay, so you have 2 inquiries. So this is what the question. So you can see that everything is in terms of seconds, not in minutes. So we have to convert our arrival rate. That means arrival rate is 15 inquiries in 1 minute. That means 15 inquiries in 60 seconds. So this is the arrival rate. So it is nothing but 1/4. Okay, so you want to find, there are 3 inquiries in this duration, 3 arrivals here, and you are talking about how many arrivals here? 2 arrivals here. So we have to just use this concept. Okay, so you can see here the probability of x of t, that means x of 10, that means x of 10 means it is starting from 0. So x of 10 minus 0 is nothing but 3, and what you want, it is showing, and 2 inquiries, x of last 15 minutes, means x of 60 minus 45 takes the value 2. This is what my question. So it's very simple. It is nothing but the probability that x of 10 minus 0 is 10 is equal to 3, and x of 60 minus 45, x of 15 is equal to 2. Since these 2 intervals, that means we are talking about the first 10 second and the last 15 second. This is 60th minute, that means 45. So the last 15 seconds and this is the first 10 second. All these intervals are independent. I told you all these are independent. So we just need to multiply the probabilities. So this is nothing but the probability that x of 10 is equal to 3 multiplied with the probability that x of 15 is equal to 2. How to obtain this? We have seen this. So that's it. So what is the Poisson process? So you know this distribution. From this we can easily substitute. That means 10 lambda t. So we need lambda t. This is our general formula, lambda t. So what is our lambda? Our lambda is 1/4. We have already got it as 1 by 4. This is our lambda. So that means number of calls. This is the number of lambda, means 1 by 4 calls per second. Okay, this is our arrival rate, calls per second. So we have, it is lambda t, so lambda into t is 10. Okay, the whole raised to k, that means k is 3 here. This is our k and this is our t here. In this case, this is our t and this is our k here. Okay, so it's very easy. So divided by k factorial, that means 3 factorial into e power minus lambda t. Lambda is 1 by 4 into 10. Okay, this is our first, multiplied with, next is lambda t. Lambda is 1 by 4 into 15. T is 15 here, and we are talking about 2 arrivals. K is 2 here, divided by 2 factorial multiplied with e power minus 15 by 4. Okay, 15 by 4 means it is 1 by 4 into 15. Okay, 1 by 4 into 15. Okay, 1 by 4 into 15. That's it. So if we calculate this, that will be our answer. Okay, so I am not going to calculate. So this is our answer. So this is our answer. Okay, I hope you got it. Thank you.